Hi, this is week 11 lecture recording video for the time series regression analysis. And we are going to perform some forecasting using the time series regression. And this is going to be the last lecture video for the semester. So first of all, presenting the time series data. So far, you have seen all those data set that has been recorded in an Excel file, and you have seen many rows and many columns. Each rows represent the observation, and each columns represent the variables. So you have seen the cross-sectional data where the data has been collected at a given point in time, and there are many variables and many observations. So each row represents the observation. So total number of rows would be the total number of sample size, and the total number of columns would be the total number of the variables you have from the data set. Another type of data set that you might see is the time series data, where each row represents the time and each column represents the variable. But for time series data in this unit, you are going to have only one data for the dependent variable, and each row represents time frame. So mostly we have been using the regression to look at how one variable affects another. For example, in the previous lecture videos, I have shown how the years of education affect income. Right. So those are using the cross-sectional data. So when you are performing a regression analysis using cross-sectional data, usually you are interested in the causality of one particular variable and how does it affect the dependent variable, right, while holding other variables constant in a multilinear regression. Another important use of regression is as a tool for prediction and forecasting. So prediction is the predictive value of using the estimated regression analysis from the one that used the cross-sectional data, right? So you substitute the values that you wish to calculate for the independent variable, and then you can calculate the predictive value of the dependent variable. Whereas when you're using the time series data, you are forecasting what the value of y is going to be with a given time that you wish to find out. Forecasting is important for time series data, and this data is that is indexed by time. For example, how the production changes over time, changes in unemployment, sales, inflation, interest rate, prices, all those you will be able to see when you use the time series data. So this is the example, right? The example I brought here is using the data for GDP growth for the G7 countries. So the most popular visualization technique to present the time series data is line chart, because all the data are connected. It flows over time. So the x-axis represents the time, and y-axis represents the value of the dependent variable, or value of y. So in this case, it's measured in terms of percentage. So the diagram below shows the time series data of annual GDP growth rate, change of G7 countries over time, collected from 1962 and until 2020. So here we represent each observation by T. Compared to cross-sectional data, for each row you represent it by subscript of I. So xi, and if I is 100, you are talking about 100th observation of that particular variable, whereas when t is used, it represents you're using the time series data, and when t is equals to 1, in this case, it refers to 1962, since the data is collected from 1962. Right, and when t is equals to 2, then it's going to be 1963. How do I know whether it increased by extra year when time increased by 1? Because the data is the annual data, right? The data has been collected annually, so there is a 1 point of the data for each year, right? So t starts from 1 all the way until the end. That represents the sample size. of the time series data. Here, you will see more fluctuations, more minor fluctuations. The diagram below shows the time series data of now. We are using quarterly data, quarterly GDP growth rate, change of G7 countries over time. So the data is collected from 1962 quarter two, right? It indicates a quarter because the data is collected every quarter, and all the way until 2019 quarter two. So when t is equals to 1, it refers to data when it is 1962 quarter two. When t is equals to 2, then it refers to 1962 quarter three, which is the next quarter, quarter three. Right, we are actually using the same data. The only difference is that the previous slide, it shows the line chart of G7 GDP annual growth rate change. And here it shows the quarterly growth rate change. So G7 is the top 7 countries which have the most economic power in the world. So if you compare these two diagrams, the patterns are mostly similar, right? Patterns are mostly similar, but the difference is that the quarterly data shows more information, right? Here you do see some fluctuation, but it's much smoother compared to the quarterly data. I will explain now why the quarterly data shows more minor fluctuations. So when you are dealing with time series data, there are 4 types of time series component. All the time series data, it has 4 components. It may exist, it may not exist, but usually we focus on those 4 components of the time series data. So the first thing is the trend, right? You might have heard about trend many times, even before you learn statistics. So this is the trend, right? Trend is upward, trend is downward, right? The one that you are wearing at the moment is in the trend. So trend it represents the persistence of the data or long-term upward or downward pattern of the movement of the data. The duration of a trend is usually several years. The source of such a trend might be gradual or ongoing changes in technology, population, wealth, and etc. So there is a particular reason why such a data is showing increasing or decreasing trend. So if you look at here, there is a downward trend, right? If you look at this graph overall, right? In 1962, 1964, in the early time of the data, right? The annual growth rate change for G7 countries for the GDP was around 5 to 6%, where now in the more recent years, it is much lower. So you do see a downward trend. Right? So the observation of the trend is quite obvious in this case. Our same logic applies to the quarterly growth rate change. Right? There is a tendency of the data that is decreasing over time. When you are trying to interpret this line chart for the time series data, usually we move from left to right because time flows from the past until the present. Next component is the cyclical pattern. We call it cycle. A cycle is a pattern of up and down swings that tend to repeat every 2 to 10 years. Okay, they have period of contraction, and there is a point leading to peak. Right? So there is a boom in the economy, then contractions with the cycle, then repeating itself. So if you see GDP growth rate just now, it shows up and down, and it was generally decreasing. So the overall pattern, overall direction of this data is decreasing. That is a trend. And you do see some up and down where country experience a recession, right? And then it experienced some depression. And then it joins the recovery, or you can say boom, and then it reaches the peak and then goes down again. So cyclical pattern is usually observed in the data due to the economic cycle or business cycle. Okay, so cyclical fluctuation are evident that relates to the state of the economy. So any particular event that happens over a period of time, then it might affect the state of the economy of the for the particular country or overall. For example, here I have shown energy crisis in 1973 to 1979, global financial crisis in 2008 and 9, and COVID-19 from 2000, and hopefully it finishes as soon as possible, but we don't know until when. So if you look at the GDP growth rate change for G7, right, 1973 to 1976, there is a huge decrease in the percentage of the growth rate for G7 countries. So this V shape is caused by the energy crisis, where there's another V shape of the growth rate change. This is due to the global financial crisis, and 2020 most likely is due to COVID-19. However, the cyclic pattern is usually observed in every 2 to 10 years. So this is more like a long-term cycle, whereas seasonality is more like a systematic and short-term cycle that happens or that repeats every year, right, within a year. A seasonal pattern is a regular pattern of fluctuations that occur within which year. So the key point here is the systematic fluctuation that is observed within each year and tends to repeat over time. So if we are dealing with the quarterly data, right, in quarter one, the data, whatever data we use, let's say it shows this kind of pattern. That this is that the start of the data is from quarter one, and then it reaches peak at quarter three. This is quarter two. It starts from quarter one, which is the lowest level, and it decreases at quarter four, and then quarter one. And every year we do see similar pattern, right? So there is an ups and down that is observed within each year and over time, right? This is observed repeatedly. So these are indication of the seasonality of the time series. All right, so this is the third component of the time series data. And seasonality is usually observed when you are dealing with quarterly data or monthly data. All right, these two are the common frequency of the data set. Just now I mentioned about frequency. Frequency of the time series data means how many data point has been collected within a year. So if the frequency is 4, right, that means the data set is a quarterly data. 4 data points has been collected within a year. If the frequency is 12, that means the data has been collected 12 times within a year. So it is a monthly data, and when the frequency is equals to 1, that means it refers to the annual data. Only one data point has been collected for each year. So for seasonality is observed any repeated pattern that happens within each year. So if you are dealing with annual data, you don't know what happened between years, since the data is only collected once in a year. Therefore, you do not observe any seasonality or any seasonal component in an annual data. So if you look at this time series plot, all those fluctuations up and down, right, all those fluctuations that you observe here is not because of the seasonal component, it's mostly due to the cyclical component. Whereas here you do see more minor ups and downs. So all those small fluctuations are due to seasonal component, but the big fluctuation is caused by the cyclical pattern. And lastly, the final time series component is irregular patterns. This is somewhat similar to the error term in the typical linear regression that you have learned so far. So this component represents whatever is left over, whatever it is not explained by trend, seasonal component, and cyclical component. Those are all called irregular pattern. Right? Things that cannot be explained by the rest of the three components. Right? So time series component, if you have trend and if you observe seasonality and if you observe cyclical pattern, most likely you are able to analyze the pattern of the data set, pattern of the time series data set, and whatever it is left out that is unexplained by those three time series components, those are all called irregular component. So modeling the trend. So if you have the data set for the time series data, usually it looks like the picture here where you have the data set. Let me call this Y variable, where it represents the production of the beer and it has been collected every quarter. So if you look at the name of each row, it starts from March, June, September, and December within the year of 1974. So there are 4 data points within a year, so the frequency is equals to 4. Hence, this is the quarterly data, right? And it is the same for 1975, 1976, and so on. And the range of the data set, right, is start from 1974 quarter 1 until 2010 quarter 2. So the time series data looks relatively simple compared to the cross-sectional data that you have used so far, because in a cross-sectional data, you have multiple columns. You have number of rows for the sample size, and you have multiple columns for the dependent variable and independent variables. But for time series data, usually you only have one column of the data, which is the dependent variable. By observing the figures, we cannot guess how the variable behaves, right? You do see the earlier part of the data set shows 465, 445, 450, right? Whereas the recent data set, it shows 488, 414. Right? By looking at the numerical values, it's quite hard to draw a picture how it looks like. So we draw a line chart. So this is the default line chart or line graph using the Excel, right? And this is how the data looks like. Right? You do see many spikes over the time. So each data point represents each quarter. So here, we need to identify the 4 components of the time series, 4 components of time series data. First is trend. Second is seasonality. The third one is cycle or cyclical pattern, and irregular pattern. Irregular pattern. So here, how about the trend? Right? Is there any general upward trend or any downward trend over time? It's quite hard to tell. Right? Some might say that there is a downward trend, that the data fluctuates around the value of 500 during 1970s, but in the most recent data set, it fluctuates around 450. So the trend may not be very steep, but there is a still downward trend. Or you might say, well, there is not much difference if I just draw a horizontal line, that it includes all the data points. So I cannot say the trend is very significant or the trend is very strong. So this is debatable. Seasonality, since we are dealing with the quarterly data, right, most likely it will include some seasonal component. So you do see ups and downs that happens every year. So if I cut the data point that repeats every year, you do see some spike that happens every year, each year. So there is a presence of the seasonal component. Right, in quarter 1, it is at the lowest, and quarter 2, it increases, quarter 3, it reaches peak, and quarter 4, it comes down. So if you look at the data set here, right, it reaches the minimum point at quarter two, it increases to the peak at quarter four, and then start to decrease until quarter three, and then increase back, right? So if you're looking at the numerical figures, it's quite hard to identify any particular repeated pattern, but if you visualize it, then it is much easier to see that you do see systematic spikes that happens each year. So there is a seasonal component. Cyclical pattern is more like a long-term ups and downs, but here I do not see any big fluctuation that happens over 5 years or over 10 years. Okay, so cyclical component, most likely I do not observe here. An irregular pattern, well, the trend, just now I say trend, questionable, we are not so sure. Seasonality, we do have a seasonal component. Cyclical, I do not think so. So whatever is left over to explain this data set is all in the irregular pattern. So no matter which time series data you are dealing with, there is always an irregular pattern. Okay, trend, seasonal component, and cyclical component, it may exist, it may not exist, but irregular component, it always do exist because all these three cannot explain 100% of the data set. So what I have done just now regarding the to deal with the trend, right? Previously, the trend component was questionable because if someone say that there is no particular trend, well, it can be still argued or it can be still accepted, right? Depends on different perspective. So what I did was we don't have any data set for lower scale. From 0 all the way up to 350, I do not have any data point, right? So what I did was I rescaled the y-axis, that I remove the lower value of y-axis. Then this is what happened, that the lowest limit is the 350 and so on. And now, of course, it feels like data has been zoomed in and it feels like there is a downward trend, right? So it depends on how you zoom in and zoom out the data. So you also need to think about rescaling the y-axis. So from here, compared to the previous line chart, it seems like the trend is more visible. It appears that there is a downward trend. So the best way to confirm whether this trend is really acceptable or not, we can run a regression and test statistical significance. Just like when you're dealing with cross-sectional data, you have multiple linear regression. And if you want to see the effect of one particular variable is significant on predicting or on estimating the dependent variable, you have gone through the hypothesis testing to see whether it is statistically significant or not. Same logic here. You have the data set Y, which is the quarterly bioproduction measured in megaliters. And you want to see that the trend component, I want to explain this data set using the regression model. And I want to see whether trend is statistically significant and is important to predict the dependent variable. So in this case, since you're dealing with time series data, prediction is actually equals to forecasting. All right. So if I want to forecast the future value of the quarterly bioproduction, do I need to take into account of the trend of this data set? Right. So if the trend is statistically significant, then you have to concern or you have to take into account of the trend component, how the data changes over time. All right. And if the trend is statistically insignificant, that means the data does not increase or decrease over time, over long run. Right. Therefore, you don't need to concern about the trend effect of the trend component for the forecasting. So here I have written the population model using the time series data. Note that the only difference compared to the simple linear regression before is that our subscript has changed from I to T since you are dealing with the time series data. And here I have variable T, okay? I have a variable T. This variable is actually created by users. So if you look at the data set here, you only have one particular variable, which is the dependent variable. I just mentioned that I want to call this as a Y variable, dependent variable, or the one that I'm trying to forecast. So since I have only one variable, which is our dependent variable in regression model, I do not have any independent variable. So here, what users of the regression analysis should do is to create a one variable called t. Right? I just call it t. So the t represents the time. Okay, so we know that the first data point, March 1974, the quarter one of the 1974 is the first data point of the data set. Therefore, I call it t is equals to 1. And the June quarter two is 2, 3, 4. And then you just highlight and double click the right bottom corner of the cell, then it will automatically fill up all the data. Right? So we do have an artificial variable called t that is created by the users, and we can use this as an independent variable. So what the regression model does is the interpretation is similar, or the logic is actually the same as the regression model that you have seen before. How do we usually interpret the beta 1 hat? Right, when the x variable increased by 1 unit, y changed by the beta 1 hat on average. In this case, I don't need to hold any other variable constant because I only have one particular variable. It's a simple linear regression. I don't need to hold other variable constant. So here it means when t increase by 1 unit as time goes by for the next quarter, the time increased by 1 quarter, how much does the dependent variable beer production measured in megaliters change on average? Okay, so after the estimation, I get this result. The beer production hat, which is y hat, equals to 498 megaliters minus 0.555 t. So as t increased by 1 unit, okay, the estimated value of the beer production decreases for every quarter. So here, this is how I interpret. The intercept is when the value of the independent variables takes the value of 0. So here we have one simple variable, y is equals to beta dot plus beta 1, right? I'm trying to write the estimate equation, and I have t. I don't have an error term because it's the estimated equation. So beta naught hat is the value of y hat when t is equals to 0, right? Note that our t was equals to 1 for the first data point, which is 1974 quarter 1, March 1974. So if t is equals to 0, right? You know what t is equals to 2. T is equals to 2 when is 1974 quarter 2. So when t is equal to 0, you actually goes back to the past, 1973 quarter 4. So the average value or the estimated value of the beer production measured in megaliters for 1973 quarter 4 is 498 megaliters, right? So it is estimated that the beer production is 498 megaliters in the past, 1973 quarter 4. This is when t is equals to 0. Okay, so the estimated coefficient of the t, negative 0.555, this is the change in y, right, which is our beer production, for 1 unit change in x. So in this case, x increases by 1 unit for each quarter, right? So we say the model estimate or the model predicts that the average beer production is to be declined by 0.56 megaliters for every quarter, per quarter. As quarter increase, right, for the next quarter, the model estimates that the beer production will decrease by 0.56 megaliters. For the following quarter, it also estimated to decline by 0.56 megaliters, and so on. So now regression can be used to capture the seasonal component. For this unit, we are not going to handle with a cyclical pattern because cyclical pattern is usually unpredictable, and it is observed due to the business cycle, and business cycle is not something systematic, right? Sometimes the up and down in the state of economy might happen in every 5 years, or it might happen in every 10 years. We never know. So the dealing with cyclical pattern is actually considered at a higher level of econometrics. But for at this moment, you are going to deal with the trend and seasonal component, right? We are trying to capture the trend and seasonal component using the regression. So in a previous simple linear regression, we only included one independent variable, which is time trend t. Okay, so when you want to incorporate the seasonal component, you have to run multiple linear regression. So the previous model is not really adequate if you want to make a forecast, because the trend only shows a straight line. And you do see that the red line, yes, it shows the general tendency of the data. But how about the magnitude of those fluctuations? It goes up and down. All right, so if you want to make more accurate forecast, you have to incorporate the seasonal component. Previously, we have seen that this data set might have trend, but for seasonal component, we were quite sure that we need to incorporate the seasonal component if we want to interpret this data. Okay, so here I have included the time trend t to capture the trend. I have included the dummy variables to capture the seasonality. Since the frequency is equals to 4, I create 4 dummy variables. Right? When quarter is equals to 1, then is equals to 1, 0 otherwise. When quarter is equals to 2, when quarter 2 is equals to 1, that means the data set is collected at quarter 2, otherwise 0, and so on. So if you want to run a regression, there are 4 quarters within a year. Therefore, I need to omit 1. Just like multiple linear regression that you learned in the previous week, if you are trying to deal with any categorical data, or if you want to include dummy variables in the model, you need to omit at least 1 variable out as a base dummy variable. Okay, so in this case, I have omitted quarter 4. So the effect of the quarter 4 is inside the estimated value of beta naught or beta naught hat. So here, quarter 1 t is a dummy variable that takes the value of 1 if the observation falls in the first quarter of each year. Okay, so the data set looks like this. So here we have the original data set, which is y, and the rest is created by users. All right, you need to create these data set. And it's very simple because t, the first data point is always t is equal to 1 and just increases by order. And quarter 1, quarter 2, quarter 3, and quarter 4, these dummy variables, I just create based on matching the data when it is collected. So for the first data point, when t is equals to 1, then it refers to quarter 1. So you put 1 for the quarter 1, 0 for the rest of the dummy variables, quarterly dummy variables. For the second data point, t is equals to 2, then it refers to the second quarter. So 1 is given for quarter 2, the rest quarterly dummy variables are 0. So you just fill up for the first year, and then you can just copy all the way down until the last observation. Okay, so it's quite pretty simple to create all those dummy variables, right? We for sure, we know that the time does not get mixed. It's impossible that we have quarter 1 and the next year is quarter 4 and then it becomes quarter 2. No, it doesn't work in that way. Since we are dealing with the time series data, it always follows the time, quarter 1, then the next data point has to be quarter 2, and so on. So I included all those quarterly dummy variables. So here I have beer production measured in megaliters, and I have the intercept, and I have the estimated coefficient multiplied by the time trend to capture the effect of the trend. And then I have the quarterly dummy variables to capture the seasonal component. Those are estimated coefficient as well. And if you look at the p-value, if you look at the p-value of the time trend t, it is lower than 0.05. The how we perform the hypothesis is exactly the same. You go through the 4 steps to see whether it's statistically significant. So all the p-values for time trend t and all the quarterly dummy variables are statistically significant. It's all lower than 0.05. Therefore, we can proceed to interpret what each of the estimated coefficients represent. So beta naught hat, or beta naught hat, we know this is the estimated value of y when t is equal to 0. Okay, the estimated beer production in time trend is, or t is equal to 0, which refers to 1973 quarter 4, is 572.59 megaliters. Right, this value is somewhat different from what you get from the simple linear regression. You got 498 megaliters, whereas here you have 572 megaliters. The gap is quite big because in the simple linear regression, we only estimate the trend, right? Whereas here we have incorporated the seasonal component. Therefore, we might expect that the beer production in quarter 4 is usually higher, or it is the highest within a year. So the predicted value or the forecasted value or the estimated value of the 1973 quarter 4 when t is equal to 0 is 572.59 megaliters. Beta 1 hat is the estimated coefficient of the t, variable t, which represents the time trend. The estimated average change, note that this is average change in beer production is to be declined by 0.56 megaliters per quarter, right? Because each data point represents the following quarters after adjusting the seasonal component, after adjusting seasonal variation. So this phrase is actually equals to holding other variables constant. Right? When you interpret the multiple linear regression using cross-sectional data, we usually say hold other variables constant, hold other independent variables constant. So here, all other independent variables are the seasonal dummies, or seasonal quarterly dummies. Therefore, I am holding the seasonal variation constant. Assume that there is no seasonal component, or assume that I control all the seasonal component. Then for each quarter, the estimated change, average change in beer production is to be declined by 0.56 megaliters. Beta 2 hat is the coefficient or estimated coefficient of the quarter 1, right? Beta 2 hat is the estimated coefficient of quarter 1. And our base dummy or base variable is quarter 4. So whenever you are interpreting the estimated coefficient of the quarterly dummy variables, you are directly comparing against quarter 4. So we estimate that the beer production in the first quarter of each year, right, since the variable is the quarter 1, we estimate the beer production in the first quarter of each year are typically means on average 74.78 megaliters lower or below compared to quarter 4, right? After adjusting for the trend. In this case, we are trying to interpret the seasonal component. So beta 2 hat, beta 3 hat, beta 4 hat, those are actually one set. All these 3 variables or all these 3 estimated coefficients are the respective estimated coefficient of the seasonal component. So what you are holding now is the effect of the trend. So you are adjusting the trend. Okay, say similar logic for beta 3 hat and beta 4 hat. Beta 3 hat, the coefficient is negative 117.2. Therefore, for every quarter 2, the average, on average, the quarter 2 beer production is typically lower than quarter 4 beer production by 117.2 megaliters. And lastly, the estimated coefficient of quarter 3, this estimates how much the beer production is typically lower or higher compared to quarter 4. So typically it is 103.95 megaliters lower than it would be in the quarter 4 after adjusting the trend. right? The logic of interpretation is all the same. It's just that now we are dealing with the time series data, and the variables that you are including is to capture the effect of trend and seasonality. Therefore, instead of saying holding other variables constant for the time series data, you are saying adjusting the seasonal variation or adjusting the trend. So all the purpose of interpretation and running the estimated regression model is to obtain the forecasted value. So once the model is prepared, that you have seen the p-value are all lower than 0.05 for the trend and seasonal component, therefore you can actually use this model to make a prediction. So when t is equals to 1, the data was when was this? 1974 quarter 1. 1974 quarter 1, right? And the data has been collected all the way until second quarter of 2010, right? Which is t is equals to 146, right? So we have the data set. The sample size is 146. We have the data set ranging from 1974 quarter 1 all the way until 2010 quarter 2. So now the last data point, 2010 quarter 2, the corresponding t value is 147. Now what I want to try to forecast is the next value, 2010 quarter 3, 2010 quarter 4, 2011 quarter 1, and so on. All right? And the corresponding t value is going to be 147, 148, 149, and respectively. So the third quarter of 2010 is where the t value takes 147. So you substitute 147 to the variable t, right? We have y is equals to beta naught plus beta 1t plus beta 2 quarter 1t plus beta 3 quarter 3t, quarter 2t plus beta 4 quarter 3t. So when the t takes the value of 147, it refers to the third quarter of 2010. So here I substitute 147. This is for quarter 3. Therefore, I substitute 0 for quarter 1, substitute 0 for quarter 2, and substitute 1 for quarter 3. And then you can obtain the value. The same logic follows for the forecasting the estimated value or forecasting the predicted value of the beer production in the future. If you want to forecast when t is equals to 148, you just substitute 148. Here, I do not have additional calculation because base dummy is quarter 4. Right? The effect of quarter 4 is already implemented inside the intercept. But for quarter 1, quarter 2, quarter 3, for quarter 1, quarter 2, quarter 3, when you're trying to make a forecast, you have to substitute value of 1 into the respective estimated coefficient. So here, using the Excel, I have multiplied the estimated coefficient of the trend with the appropriate value of t, and also substituted a value of 1 for the respective quarter and 0 for all other quarterly variables. And by the substitution, and if you draw the value, the blue line shows our original data, whereas the orange line is the one that I calculated or I actually forecasted using the estimated model. And it seems like the forecasted value somewhat behaves nicely compared to the original data. Now, when you are forecasting, there is a something called in and out of sample forecast. So in sample forecast, or if we say in sample, we are actually utilizing the data that you have. This is the data we have. And out of sample forecast is to forecast the data that we do not have. if we have an estimated model, and we can actually substitute the value of the data set that we already have. Okay, although you have generated forecasted model and the forecasted values appears to be consistent with the data, we can examine of the goodness of fit of the model by comparing predicted values with actual values over time. So if you look at the regression output model, you notice that R square value is pretty high, 0.88. And if you have a systematic data like this, and the only thing that you observe for the pattern of this data is the trend component and seasonal component. Of course, if you capture all those time series data component, then most likely your model fit would be good. So the R square value is going to be very high. It's going to be very close to 1. This is very typical when you are dealing with time series data. Whereas cross-sectional data, you are trying to make a prediction using multiple independent variables. R square value is not this high, all right, because finding the causality is more complicated using the multiple variables. But for the time series data, it is quite easy to make a forecast, or the regression model provides quite good fitness if you can capture trend and the seasonal component. I mean, of course, it depends on how the data behaves. If the data seems like there is no trend and there is no seasonal component, there is no cyclical component, if it feels like it's just full of irregular pattern, that means it's hard to forecast anyway. So the goodness of fit of the regression model is going to be very low. So we can actually see the goodness of the fit of the time series data using the data that we already have, right? We already know the value of t is equals to 1, t is equals to 2, all the way until t is equals to 146. And we have beer production in megaliters all the way until the end. If we have the actual data, why do we even bother to make a forecast of this period, right? I can substitute the value of, I can actually substitute the estimated model with respective t and these quarterly dummies using the estimated model, and then I can make a forecast for the data set that we already have. So this is going to be within or in sample forecast. Okay. The purpose is to see whether our model generate a good forecast value or not. It's good to try to fit the estimated model for the data set we already have. And if you notice that the actual data and within sample forecast value are very close together or almost same, that means that the estimated model that you have created actually captures the pattern of the time series data very well. Therefore, you would have greater confidence to make a forecast using the data. Okay. Whereas if your in-sample forecast deviates much from the actual data set, just like y and y hat, it refers to the residual. And if the residual is big, right, if the discrepancy between the within sample forecast and the actual data is large, then of course, your forecast may not be accurate. And one of the main reasons why we do this is because usually in a cross-sectional data, it is good to have more sample, right? The more the sample we have, then our estimated coefficient is going to be more unbiased and it's going to be more consistent, right? Since we have learned in the sampling distribution, as long as we have sufficient sample data, right? As long as we have a sufficient observation for the data set, then our estimate is going to be quite accurate and standard error is low and is statistically significant. All right, when you are dealing with the time series data, it is actually not always correct or it's not always accurate to include many data sets. What I'm saying is you are trying to make a forecast for the future value. You're trying to make a forecast for the future value. And if you want to maximize the sample data that you want to utilize, and you collect or you use all the data set that has been collected 100 years ago. And if you're trying to make a forecast what is going to happen for tomorrow, the data that you have for 100 years ago may not be really relevant and may not be really useful. So sometimes it is wise to delete the old data. So you can generate in-sample forecast using the estimated coefficient from t is equals to 1, just like calculating y hat when t is equals to 1 and so on. Okay, so the forecast value you produce out of the data range starting from 2010 quarter 3 when t is equal to 147, the data that you don't have, right, those are out of sample forecast. So this is the overlap of the within sample forecast or in sample forecast and out of sample forecast. And the blue line shows the actual data. The orange line shows the our y hat, which is the estimated value of beer production. So orange line all the way until here, these are in sample forecast. So y hat t is equals to 1 all the way until y hat t is equals to 146, all right? Whereas the orange line that does not have a blue line, these are out of sample forecast, where you are trying to put y hat t is equals to 147 all the way until y hat 151, right? Because I just forecast it for 1 year, 4 quarters. Okay, so you do notice that the orange line mostly overlaps well for the old data, but you notice that there are some blue lines that is beyond or higher or lower than the within sample forecast. So in this case, you might want to observe what happened. Why was the peak particularly high in between 1988 until 1992? So this is where your research skill comes, that you have to drill into the nature of the data. What happened to the quarterly beer production in 1988 until 1922? Why was the peak much higher? Was there any change in the legislation? Maybe they lowered the age restriction from 19 years old to 18 years old for this particular country, right? So it depends, right? So you have to see that our model mostly captures well. Our in-sample forecast captures the general pattern of our data set, even for the early part in 1970s, but there was some irregular pattern observed that is not explained by the regression model, especially in late 1980s, where the beer production peak in quarter 4 was much higher than our estimated value. Okay. Usually, more available data is seen good, right? Usually we say more data is good, but it may not necessarily true for forecasting because sometimes we do not want to have the old data set. So the purpose of developing forecasting model or purpose of running a regression model of using the time series data, usually the focus is on forecasting and obviously focus on generating the most accurate forecast for the future. What is the point of accurately matching or accurately estimating the in-sample forecast, which was 30 years ago, right? That's not our objective. Our objective is just to create or generate the most accurate forecasted value for the future, right? Having too little data can be problematic, but including too old data might disturb the accuracy of the estimated coefficient because I don't want to see the data that has been collected 1950s or 1960s. Right, because our life depends on the nature of the data, but the things around us has been changed a lot. Okay, so here we have two estimated model. The first estimated model is the one that you've seen before, and the second estimated model, the sample size has been decreased to 42. Previously, the sample size was 146. Okay, all the way from 1974, quarter 1. But now the data, I only use the data starting from 2000, year 2000. All right. So this is the estimated value. This is the estimated coefficient of the regression model when the data has been manipulated. Data has been reframed that it started from 2000 quarter one. Okay, so this is when we have the data from 1974 quarter one, right? And the second one, we have 2000. So if you are trying to make a forecast, of course, the general pattern behaves similarly, right? So the orange line shows the forecasted value using only the recent data that has been cut off from 2000, whereas the blue line shows the full data forecast, where I use all the data available since 1974, right? So even though these two curves might seem very similar, you might need to consider whether you should cut off the data or not. In this case, it doesn't show much difference because the general behavior of the pattern was very similar all the way from t is equals to 1 until the end. But if you have the data set that changes over time, for example, here on the right-hand side, here I have the data set of the liquor expenditure or in Victorian state. Okay, we have a peak in quarter 4 and the lowest level for quarter 2. In earlier part, 1995 or 1990s, there is a seasonal component, but the seasonal component was quite weak. That means the fluctuation was not really strong. I still do observe a similar pattern that quarter 4 is always highest and quarter 2 is always the lowest, right, throughout the data. But the difference or the fluctuation was not really strong. Whereas I do observe similar or the same pattern in the recent data, but the magnitude of the fluctuation is much bigger. So if you use your logic, try to make a forecast, of course, you're going to have up and down. You're going to have up and down. And you know that the fluctuation increases over time, there's an upward trend, and the seasonal fluctuation, it gets larger and larger. So in the future, of course, you might expect that the seasonal fluctuation for the future value might increase even more. Okay, so in this case, if I use the old data, for example, I do observe small seasonal fluctuation until 2007. Okay, I do see a seasonal fluctuation, but it's very small. I may not want to use this because these data, or these old data, might underestimate the seasonal component or seasonal variation of our future forecasted value. I might just want to forecast on the recent data because even though I use the recent data, the patterns are quite systematic and similar. The trend does not change over time. Therefore, I can include trend and seasonal component. Then most likely I will generate or produce quite accurate forecast value compared to using the whole data set. And the diagram on the left side, okay, we might want to remove the old data because of some structural break. So structural break is the particular event that changes the trend dramatically after a certain point in time. So here I have the plot for Australia unemployment rate measured in percentage from 1990s all the way until 2016. So I might notice that from 1994, there is a generally decreasing trend, but in early 1990s, it was upward, right? It was upward, reaching the peak and then start to decrease. So in this case, if I want to generate the forecasted value, I might want to remove this data. I might want to remove this data because we don't know what happened, but in 1993, Australia unemployment rate was increasing. The economy was not really doing well in Australia until 1993. But after 1994, the unemployment rate consistently decreased over time. So if you want to make a forecast, probably you might want to remove the early 1990s data. Okay, so that's all for the last lecture, and all the best for your final exams as well. Stay safe.